Hi, let us proceed with our revision questions on the column. We are in the middle of solving the questions. So far, we have done to this stage. Now, our next question, it will be designing the main reinforcement bar as well as the shelling. The columns to be designed, it will be column B3. And the column, it will be the ground floor column. Before that, let us look into the overview of the design process. It normally starts with the analysis of the load adding onto the column. In this case, we use two methods to do the analysis. First is the moment distributions method. Second, it will be the analysis based on the critical load arrangement. Both analysis will give us the axial load as well as the moment acting onto the column. Let's say we use the critical loads as the design parameters. We have the axial load of 66.24 kN and the design moment of 2.4 kN meter. If you wish to know more how those values are obtained, you may refer to our previous videos. Now that we have the axial load and the moment, the axial load you may use directly for you to compute the design reinforcement areas. However, the moment that you obtain, you cannot use directly as the design moment, since there will be other factors governing the design moment. You will need to consider those factors in order to conclude the design moment before you can determine the area of the reinforcement. Now, these other factors governing the design moment, it will be due to the type of the column, whether it is a short column or a slender column, whether it is a braced column or unbraced column. Coming back to this question, we know that it is a braced column, and then based on the slenderness analysis, we found that it is a short column. That means in order to compute the design moment, we will need to refer to the category of the short column. It is only after we've done the calculations of the design moment, put it into the equations, and find the AS required from the column design chart. With that understood, let us look into the solutions for the design of the main reinforcement. In your solutions, you are strongly recommended to sketch the stress diagram for the columns that you are designing. It can be short column, it can also be slender braced column, and it can also be slender unbraced column. The equations to determine the MED vary significantly among different categories. It may seem complicated, but if you try to sketch them, it is easy. We talked about this in our previous videos in the chapters of the column. Since now the short column is to be designed, this will be the simplest diagram that you can expect from the design of the column. Sketch the stress diagram, label the components, and then you can work out the equations to determine the MED. First, you will need to determine the M02. M02 is the bigger moment of the two moments acting at both ends of the column. Taking this question as an example, remember that previously we calculated the moment at both ends of the column. Near to the joint to the first floor, the design moment is 2.4. And near to the end of the stump, the moment is 1.9. That means we are looking at the bigger moment, as it is going to be more critical. Therefore, this 2.4 shall be the M here. We will need to add up the factors for the impurity in order to calculate the M02. This impurity is calculated by having the Asian loop times the eccentricity, EI. Try not to confuse with the eccentricity, since there are three types of eccentricity in the equations. We have EI, we have E2, and we have E0. EI is calculated on basis of the effective length. It is calculated by dividing the effective length by 400. Now, where do we get this effective length? Remember previously when we determined the slenderness of the column, we have calculated the effective length. There is a formula for us to calculate the effective length depending on type of the column, braced or unbraced. The effective length is 2.098 meter. Divided by 400, you get the EI. The calculated EI is equals to 5.2 mm. The Asian loop is 66.24 kN. Multiply with EI of 5.2 mm plus the moment acting onto the column. We are talking about the larger moment of the two, which is 2.4. Eventually, you get your M2 equals to 2.75. That means this will be 2.75. Now, if you refer to these equations, we have done determining the M02. We will need to get the M mean, where the bigger value of the two shall be the MED that you use to determine the reinforcement. The M mean, it will be meant for the construction tolerance. It is calculated using the NED times E0. The E0 here is calculated on basis of the column size. The formula for the E0s, it would be H per 30, where the E0 should be at least more than 20. The H here refers to the column size, which is given in the questions 200 times 200. Therefore, you will take 200 divided by 30, it gives you 6.7 mm. The equation states it needs to be at least 20. When the calculated value is less than 20, you will use E0 equals to 20. Now you calculate the M mean. NED is equals to 66.24 kN. E0 is now 20 mm. That gives you M mean of 1.32. Substitute the value into the equations. The bigger value, it will be the MED. Now that you have determined the NED and NED, you have the properties of the columns and the dimensions of the columns. Substitute all the values. You will need to find the AS FYK per BH FCK from the column design chart. And this whole thing here are non-value except AS. Once you get this value here, you are able to determine the AS, representing the area of reinforcement in the column. So we are going to do the calculations and apply the column design chart. NED is 66.24. BH represents the column size, 200 times 200. FCK represents the concrete strength, which in these questions, the FCK is equals to 30 Newton per mm square. The calculated value equals to 0.055. You will do the same for the M per BH square FCK. The M now, it will be the MED that you have calculated, which is 2.75 kilonewton meter, divided by B, 200, times H, 200 square, and FCK, 30. You get this value. The next step, it will be referring to the column design chart. In fact, there are quite a numbers of column design chart. You will need to look at the D per H ratio. Use the suitable column design chart in accordance to its D per H ratio. In order to decide which column design chart to be used, you will need to first compute the D over H. The D over H is referring to this D over the H here. It is calculated by the concrete cover plus the size of the shear link plus half size of the reinforcement bar, as implied by the equation here. The concrete cover is 30 as given in the question. The size of the link is also given at mm. And the proposed size of the reinforcement bar, it will be 12 mm. You will have 30 plus 8 plus 12 mm divided by 2. That gives you D equals to 44. Divided by the H of the column, which is 200. You will have the D per H ratio equals to 0.22. Among the design chart, there is no design chart for 0.22. However, we have the design chart of 0.2 and 0.25. Theoretically, in order for you to determine the amount of reinforcement bar, you will have to refer to the both design chart, and then whatever values that you obtain from both charts, interpolate them to the D per H equals to 0.22. With that understood, let us look into the chart. We first deal with the D over H equals to 0.2. The y-axis represents the NED divided by BH FCK, and the x-axis, it will be due to the moment. Find the relevant value. 0.0552, it will be represented by this line, and 0.0115, it will be represented by this line. The two lines intersect at this region here, which theoretically the ratio of AS FYK per BH FCK is less than 0. That means no reinforcement bar shall be required. The column size is relatively large as compared to the load acting onto it, and then the moment is relatively small, which when the column is subjected to compression, the flexural crack is not likely. Next, we will do the same for the chart of DH equals to 0.25. Again, it intersects at the region without any reinforcement. You do interpolations, you know that no reinforcement bar shall be required. However, in the design of reinforced concrete structure, we cannot simply put entire column purely concrete without any reinforcement. When we calculated the reinforcement bar is not required, that means the amount of reinforcement bar shall be governed by the minimum AS. Therefore, our next step is to calculate the minimum AS. This is the equations for the minimum AS. In the functions of the absolute divided by Fyk. The absolute is 66.24, and the Fyk, it will be the grade of the reinforcement. According to the questions, Fyk equals to 500. Substitute those values, and you will need to make sure that whatever value computed here, it will be at least 0.002 area of the column. That means you are checking two values in order for you to get the AS mean. The AC here is determined by 200 times 200, which is the size of the column, and it gives you have AS minimum of 15 mm square. Very minimal. In another word, the calculated AS required, it will be 0. But you know that definitely you cannot put pure concrete without any reinforcement. Now you do the checking for the AS mean. The AS mean gives you 15 mm square only. Theoretically, the AS mean will determine the amount of reinforcement bar provided. As long as you provide the rebar area more than this, it is theoretically adequate. However, there are other considerations. First, for a typical column design, you will need at least 4 reinforcements, 1 at each corner. Why is it so? These 4 reinforcement bar shall later be tied with the shear link. Therefore, bare minimum 4 reinforcement bar. This is applicable for rectangular column. And then, for practical considerations, the bar diameter should be at least 12 mm. Therefore, bare minimum, you will need to provide 4 H12 for this column. The total bar areas, it will be 452 mm square. Even though this is significantly more than what is required, but due to practical considerations, this is the least amount of reinforcement bar that you need to provide to this column. This design is acceptable as the provided bar area is greater than what is required, and it is also greater than the AS mean. Corrections. This 15 mm square is due to this formula, whereas 0.002 AC will give you 80 mm square. That means your AS mean now, it will be 80 mm square. Still, the provided reinforcement bar is greater than AS mean, and the design is considered acceptable. Coming back to the question here, we have done calculating the reinforcement bar. Our next step is to determine the shear link. This you may refer to the slide here. These are the requirements for the shear link. The bar diameter of the shear link shall be at least 1/4 of the main reinforcement bar, or at least 6 mm. Now the main reinforcement bar provided, it will be 12 mm. Divided by 4, you get 3 mm. The minimum bar size, it will be 6 mm. Therefore, you may choose to use the mount steel 6 mm. However, if you are referring to the questions states that the shear link diameter, it will be 8 mm, which is larger than the minimum requirement of 6 mm. Therefore, the provided shear length is acceptable. Now the next step, it will be for us to decide the spacing of the shear length. There is a maximum spacing for the shear length. 4 factors are governing it. 20 times the bar diameter, which in this case the bar diameter is 12. That gives you 240. The maximum spacing is also governed by the dimensions of the column, which in this case it will be 200 and 200. Lastly, it is stated that the spacing cannot be more than 400. Choose the smallest value of all. Now you know the maximum spacing, it will be 200. Therefore, you should put your maximum spacing are at 200. On top of that, there is another requirement on the maximum spacing, particularly in the case that you need to provide shear length near to the joint, within a distant hitch from the top beam, as well as the beam soffit. The region here will have the maximum spacing multiplied by 0.6. That means the shear length, it will be more closely spaced. Now your maximum spacing is calculated equals to 200. 60% of this 200, it will be 120. Therefore, for the lapping regions or for the areas near to the joint, you will have your maximum spacing of 120.